So in this example, we're going to evaluate the integral over c of 12x ds, where c is actually the union of two curves, c1 and c2. And I gave it to you in a picture here. So c1 is actually a line, and it's the line y equals x, a line, part of that line segment anyway, between 0, 0, and 1, 1. C2 is part of a parabola y equals x squared. Actually, the way it's parameterized, it's going from 1, 1 to 0, 0. But as you'll see, when you evaluate line integrals with respect to arc length, the orientation of the curve doesn't matter. So if it's more convenient to orient it the other way, that's what we'll do. So I haven't proven it, but it shouldn't come as a big surprise that a line integral with respect to arc length is additive over the whatever set you're integrating over. So here's something I'm going to state without proof, but the line integral over c of 12x ds, it's the same as the line integral over c1 union c2. That's what c is equal to. And this is my claim. That's going to be the same as the integral over c1, 12x ds, plus the integral over c2, 12x ds. And so the idea then is we can break this up into two separate integrals. Okay, so let me try a far away view here so we can see everything. So we'll take one integral at a time. Let's take c1. We need to come up with a parameterization for c1, the line in green. And little scratch work over here. This is good for any time you're given y as a function of x. Anytime you're given y as a function of x. So in other words, y is a formula in terms of x. To get the parameterization, it's about as easy as you could hope for. You always let x equal, or t, sorry, or whatever you're calling the parameter, usually t. You're going to let that be the input. In this case, which variable represents the input? So you're always going to let your parameter be, when you can define y as a function of x, or even x as a function of y, you're always going to let the parameter be the input variable. Especially when you're in the plane, that's what this really applies to. So in this case, the input variable is x. So you're going to let x equal t, and then automatically y is f of t. And so that your vector valued function, if you want to write it that way, is just t comma f of t. And then if it's x is a function of y, let me use a different color here. If it's x as a function of y, oh, let's use g, not f again. Then what would you do? You would let y be the input, so I'd say let y equal t, but I'll put x on the left, which makes x g of t. Or in vector valued function form, r of t is g of t, t. Okay, so this is generic right here. And it's good to keep in mind. So let's focus on C1, which is given by y equals x. C1 given by y equals x. So what you guys tell me then? What is the parameterization going to look like? Yeah, I mean, it's about as simple as you could hope for here. So you're going to let x equal t, and you're going to let automatically then y equals t as well. Now, to get our limits of integration, we need to have bounds on t. The bounds on t will be our limits of integration. So you look at the line in green. If you want to keep the parameterization, the orientation of the parameterization going from 0, 0 to 1, 1, then based on what we have so far, there's only one value you can let t be so that the first point, the beginning point, is 0, 0. And what would that be? Just 0. And then what would you plug in for t to get to 1, 1 up here? 1. Now, any parameterization will work, but this is the simplest. So, all right, in terms of, okay, we'll do the vector value notation first, although you don't have to, as you'll see later on. So in terms of a vector valued function, this is r of t equals just t comma t, right? So our calculation formula for the integral over c of f ds, remember, is the integral from a to b of the, okay, it's just f, but it's f in terms of t. I'm not going to write that, but you have to remember that. You got to get it in terms of one variable, right? And then magnitude r prime of t dt. So just so you have that to refer to, because you gotta be a formula whisperer, right? What is the formula telling you to do? You don't have your steps memorized. You have certain formulas memorized, and those formulas tell you what to do. So looking at that formula from the inside out, what does it tell you you need to find? Well, the parameter first, the parameterization first of all, which we did. But then what else from that the calculation formula on the right here? What does it tell you need to find? But then look inside those magnitude bars. It tells you first find r prime. Okay, so r prime, I'll put a comma here and put r prime over here. What's r prime going to be? 1, 1. All right. And then pretty easy to find the magnitude of that, right? Magnitude r prime of t then is what? Root 2. Everybody good so far? All right, so then here's how I would notate it. Let's use the generic notation, the integral of, it was 12x ds. The integral over c1 of 12x ds, the actual calculation formula then is the integral from, what are the limits of integration? 0 to 1. 12, okay, what's x? You got to put it in terms of t. What is x? It's t. You could either look at the vector valued function version, x is t, or your parametric equation, x is t, either way. So for this x, you replace that with t. And then ds is the magnitude r prime of t dt, which is just root 2 dt. Yeah. Not a particularly difficult integral compared to what you guys have been doing, right? Okay. So bring out the 12 root 2. And I dare say we could integrate this right away, make it 1/2 t squared, right? Evaluate from 0 to 1. Everybody buy that? So what does that end up being? So 6 root 2. We're not done, right? That's just one of the two integrals we have to do. Any questions on that? Okay, so let's do the other one. That'll be a little more interesting. So let's do kind of in parallel over here, C2. C2 in function form is y equals x squared, just a certain segment of that. So you guys tell me what are our parametric equations then? Yeah, the input's x, it's y as a function of x, y equals x squared can be thought of as y as a function of x. So x equals the input t, and y is equal to whatever the formula tells you to do, square it. And then, now, I mean, that's one parameterization, and this is actually going to be the parameterization that goes from 0, 0 to 1, 1, not from 1, 1 to 0, 0. It would be more complicated to go from 1, 1 to 0, 0. In fact, I'll have you guys think about how you could actually parameterize that to work. You might have to use like 1 minus t or something. But I'll let you guys think about that. Let's just go from 0, 0 to 1, 1. It doesn't matter. You're integrating over the same set of points. ds is going to be positive. Think about what ds is. Magnitude r prime of t dt. It's positive. It's a magnitude times, yeah, it's positive, right? So the parameterization the orientation of the parameterization doesn't matter. Okay? So to go from 0, 0 then, to 1, 1, what would t have to run from? 0 to 1 again, yeah. Okay, and then once again, what does our formula tell us to find? If you think of r of t, I mean, and you don't have to write this down if you don't want to, but if you think of r of t as t comma t squared, right, as a vector valued function, what does our formula that I have circled in purple up there next to the graph tell us to do? Find r prime of t, so I'll do that right next to it. R prime of t is just going to be what? 1 comma 2t. And then we need its magnitude, don't we? So the magnitude of r prime of t, what's that going to be? Yeah, or 4t squared plus 1, either way. Let me make a better looking t there. 4t squared plus 1. Everybody okay? Okay, put it together for me then. So I'll do this part. We want now the integral over C2, remember, because we're going to end up adding these guys. And generically, that's integral over C2, 12x ds. So what's that going to be? Integral from a to b, 0 to 1, 12 times t. And then we have magnitude r prime, which is 4t squared plus 1. And then don't forget the dt on the end. But even this isn't so bad compared to what you've been doing, right? Triple integrals and whatnot. So definitely a u sub. I think I'd write the 12 out front. And then I think I'll leave the 4t squared here and put the t, leave a little space, put the t here, dt. So what would you let u equal? 4t squared plus 1, so du would be 8t. So what do I need to do to get a perfect du? So I'm going to put 8 here, but that means I have to compensate by dividing out front by 8. And now you could just think, again, we don't make the substitution on easy ones like this. You can just think of that, though, as square root of u du. That 8t dt is your du. We just don't make the substitution. Now, so, on the test, some of you did actually make the substitution. There's nothing wrong with that other than when you don't change the limits of integration, it's technically wrong, but then you substitute back and it becomes right again, so you're wrong and then you're right. It's kind of like a sine wave. You're wrong and then you're right. But it really is easier to do it this way on the more straightforward side. Sometimes you have to make the substitution and make it work, but these ones you don't. So you can just think of this as the integral of the square, without disregarding the limits of integration, the integral of the square root of u du. Okay, so what does that turn out to be? So what do we get in front? What, 12/8? So 3/2, right? 3/2, and then, okay, we integrate. Now I see what you're saying, 2/3 from that, right? And then 4t squared plus 1 to the 3/2, evaluated from 0 to 1. And we're going to leave those factors out front, right? Don't put those in the evaluation brackets. Makes life easier. Plus 3/2 times 2/3 is just 1 in this case. So what do we end up with? When we plug in 1, what do we get? So we get 5 to the 3/2. I'll simplify that in a second. And then, we have to plug in 0, right? Minus just 1. Okay. Yeah, let's not write 1 to the 3/2. Does everybody agree with that? 5 root 5, you want to call 5 to the 3/2? Okay. So then the integral over c of 12x ds would be what? 6 rad 2? So that's this guy. Plus 5 rad 5. And then was it minus 1? Okay.